Welcome everybody to today's Power Hour. I'm Ryan Koyman, Director of Training here at Standard Motor Products. And today we're going to be talking about drive-by-wire systems, specifically as it relates to electronic throttle control. Now, today's modern vehicles, we're certainly seeing more and more mechanical features being handled by electric motors. We think about that with like parking brake actuators, sunroofs. You know, we've been seeing that for years with windows, power locks, even with power steering now. And so we're seeing an electrical motor perform a mechanical function on the vehicle. And so today we are going to talk about electronic throttle controls. Why have them? What's the benefits of it? More importantly, how do we make an accurate diagnosis and determine which component needs to be replaced or wiring or software repair needs to be done? So first off, I want to talk about one of the benefits here is actually better control of the vehicle. I've got a Buick Encore here with me. We're going to be looking at a case study. We'll be diagnosing it here. But engineers for years and years have wanted to get better control of the vehicle. And so one method here is through electronic throttle control. Now, if we look at the scan data up on the screen here, you'll see the top line there is the APP, the Accelerator pedal position sensor. And so this is the driver's input, the driver request. So if you look at that scan data, you can see that it plateaus. It goes to 100%. This means the driver is, for all intents and purposes, flooring it, right? Pushing their foot all the way to the floor. They want to go fast. The second line, we see the actual throttle position. And so on old mechanical vehicles, if your foot was to the floor, it meant the throttle blade was wide open. But with today's drive-by-wire systems, we see that the PCM or the control module is ultimately in control and gradually ramps up and gives the engine as much air as it needs there. And so that's just one example of better control. Another example here is component reduction. Think specifically about cruise control. We no longer have to have a standalone servo. We don't need cables. IX, really kind of a thing in the past. And so engineers were able to reduce the amount of components required on a vehicle by incorporating it all into electronic throttle control system here. Powertrain protection. Now, not everybody likes that. Quite often they can find the traction override button. But as an engineer, they are looking to protect the powertrain on the vehicle. Transmission, rear end, whatever, tires even. And so drive-by-wire systems really takes away the consumer's ability to do a big John Force burnout on the vehicle there. Another benefit is traction control. Torque limiting is really one of the big side benefits of electronic throttle control here. And I'll talk a little bit about torque creation and torque management throughout the presentation here. But really, that's what throttle is doing. It's managing the amount of torque going to the wheels. So if a vehicle is, let's say, driving on an icy slope, as you see in the picture here, you know, that was last week in Michigan. You know, some of you up northerners will understand that. As the vehicle detects wheel slip, it's going to reduce some of the torque applied to the engine to help make sure that all four wheels are going the exact same speed. That brings me to my first power tip I want to share with you. I've seen a lot of different case studies. This is a condensed version of our full 4-hour class, but I've seen plenty of examples on forums, in shops. We've got a real case study in our class of a technician misdiagnosing electronic throttle control system. You know, the customer concern was the vehicle doesn't have the power it used to. Technician, no trouble codes, which is always frustrating for techs, but they'll diagnose the system and go, you know what, the throttle's not opening all the way here. That seems to be a problem. And so they erroneously go ahead and make the decision to replace the throttle body. Well, guess what? The problem wasn't any better with the new throttle body because the fault wasn't with the throttle body. So if you run into a situation like this, graph out and monitor all four wheel speed sensors. The examples I've seen, one wheel speed sensor will drop out. The PCM thinks that wheel is slipping or locked up or lagging behind. So it's going to reduce the amount of engine torque via the throttle command and reduce the power to the wheels. And so if you're in this situation, make sure that you're verifying that all four wheel speed sensors are in fact measuring or producing the same type of output. Another benefit here is reducing emissions. That's all the rage, right? And it has been, at least in my 40 plus years of life here. Manufacturers are continuing to look at how to clean up the tailpipe emissions here through catalytic converters. But now with electronic throttle control, engineers can help get that catalytic converter lid off and working properly that much quicker by controlling or choking off the airflow. Remember in the old days of carbureted vehicles, there was a choke device, right? Which limited the amount of airflow and it created a different fuel mixture, air fuel mixture. Engineers are really doing a lot of the same stuff now with electronic throttle control. They can control the amount of fuel going to the engine via the injectors, but they can also choke off and control the engine via the electronic throttle control to help that catalytic converter working much earlier in the drive cycle and cleaning up that tailpipe. Then another benefit here is eliminating pumping losses. Now, if you're not familiar with the term pumping losses, let me explain a little bit here. So in a four-stroke engine, we've got the pistons going up and down throughout all four strokes. Now think about the intake stroke. The piston starts at the top and it draws itself down, or it's drawn down by the crankshaft. As it's coming down, it's pulling air in through the intake valve, drawing it in to fill the cylinder. The air is going to produce a vacuum because in most cases, we've got a throttle blade at the beginning of the system, which is going to be closed in many cases. And it's going to create a vacuum. Now, this actuation or this vacuum actually is reducing horsepower, or creating a drag on the crankshaft, resulting in what's referred to as a pumping loss. Any type of inefficiency that's affecting the pumping of the engine there. And that's why diesel engines are much more efficient in many aspects, because a lot of them don't have throttle plates. Some of them, newer ones do for emissions purposes, but they're going to default to open position. And so those engines breathe much freer and easier due to no pumping losses. So where am I going with that? Engineers today with electronic throttle control can use it to their advantage. And so recently I was driving a 2.7 liter Chevy Silverado and, a full-size truck with a little four-cylinder. Of course, it's got a turbo, it's got VVT, a lot of different technologies incorporated into it. And it was amazing to see as that truck was driving steady speed down the road at 55 miles an hour, the throttle blade was commanded almost completely open. The engine RPM was being controlled via cam timing, ignition timing, injection amount, and using all these other technologies in sync with electronic throttle control system to help that vehicle breathe easy and run freely down the road as efficiently as it could. We couldn't do this with an old mechanical throttle cable style system. Here's another one that, for those of you that were working on cars in the 90s, this was commonly referred to in the shops I worked at as morning sickness. And this is a scenario in which customer predominantly with a GM 4.3 liter, think of an Astro, Chevy S10 Blazer, something along those lines. They would come in and say, first thing in the morning, man, I really got to stomp on the throttle to get the vehicle to move here. As the day goes, it seems to get better. Well, that was because of carbon buildup on the throttle blade inside the throttle body itself. And so after the vehicle sat all night, that carbon would harden itself up. And so the driver would press on the throttle and it's pulling on a cable and it's a mechanical device at this point. They have to put extra effort to break that thing free. Now, as the engine warmed up and the day went on, that would kind of turn into somewhat of a goo or more of a liquid form, and it would be much easier to actuate the throttle. Well, today's electronic drive-by-wire systems, the driver is simply pressing against a spring here, and so they're really not doing a whole lot of mechanical work. So the driver experience is much more comfortable today than it was previously. Another one is, as we look at newer technologies, they've been significantly enabled due to electronic throttle control here. So if you look at the scan data displayed on the screen, you're going to see, first off, we've got an example of a vehicle with displacement on demand. Now, again, for the, I can't say old timers necessarily, but the veterans on the meeting here today, you may remember some of the old Cadillac systems that would drop different cylinders strategically, and that was not a real raging success. Today's vehicles, quite often we'll see them go from, with displacement on demand, go from 8 cylinders to, let's say, 4 cylinders. And so, again, with electronic throttle control, The PCM knows when it's going to disable these multiple cylinders, and it's going to compensate for the adjustment in airflow via the electronic throttle control system. So it really helps complement, if you've driven any of those to modern vehicles with a displacement on demand system, it's really a seamless transition, whereas it wasn't necessarily so seamless in the older Cadillac test phases, if you will. We've also got an image of a hybrid engine there. Really, hybrid technology would really not be possible without the use of electronic throttle control. Again, it's very seamless in many cases when it goes from electric power to internal combustion engine, and it transforms back and forth. With the use of electronic throttle control, now the driver's pressing on an input device, being the APP, and they're making the request, but the PCM is ultimately controlling the internal combustion engine torque output via the throttle body. So it's really been a huge motivating factor here for a lot of newer technologies. So let's look at the system as a whole. So again, we've got the accelerator pedal position here, and this is, again, the driver input. How fast do you want to go? And maybe a dangerous question to ask some people, like my assistant, Ricky Bobby, here in the studio today. But, this is the input from the driver, pressing down on the throttle, making the request to the control module. And so earlier ones had a standalone TAC throttle actuator control module. A lot of them now is done primarily through the powertrain control module. So the module is looking at not only the input from that, but it's looking at stuff like engine coolant temp sensor, intake air temp sensor, transmission pressures, which gear is currently selected, what's the temperature of the transmission, what's the mass airflow input. It's taking a lot of these things into consideration, and that's going to ultimately make the command to the throttle body. So the throttle body's got an electric motor. I'll show you a little bit more in depth here in a couple slides. But we've got electric motor in multiple position sensors in there. So the PCM will make the command to the motor. The multiple sensors in there will give a feedback to the control module saying, okay, this is where you told me to go. This is where I'm at. And so we've got a motor and multiple throttle position sensors giving the feedback. So that's where the work is really ultimately done. So let's break it into the individual components here. And again, as we look at the APP, again, in the old days, the customer would floor it. They would be pressing the pedal all the way to the floor. It would be pulling on a cable, mechanically opening up the throttle. As I look at this Toyota example here, it's very much exposed components. So you're going to see that there's a spring in here, and that's what the customer is effectively acting against. That's the mechanical action there. Many people maybe have grown up only driving drive-by-wire vehicles now. But even for the other people that grew up driving a cable-driven vehicle, it feels very similar. Engineers have done a great job of balancing the pressure on the spring here. So the driver is simply pressing on the spring. Then there's multiple sensors. Some of these early ones definitely had 3 sensors built into them. A lot of today's newer ones will only have 2 sensors. But there's going to be multiple sensors in there for redundancy. And so earlier ones were always a resistive potentiometer, in which we got primarily analog signal. Newer ones use a Hall effect assembly in there. The output looks very much the same. So you as a technician looking at a scan tool, you're not going to go, oh, that's a potentiometer. Oh, that's a Hall effect sensor. You're not going to see that. You're going to see the voltage change the way you've always seen it change on the scan tool. Just wanted to make you aware that newer models are using Hall effect technology. There's an internal chip making sure that the output is the same, but it's much more accurate. So as we look at some of these different APP signals here, I just want to illustrate some of the examples here. So if you're not familiar with these, you understand how the sensors act against each other. So this first example here, you can see we've got 3 APP sensors or signals output from the APP assembly. The first one is going to start low voltage. As the pedal is pressed further, the voltage is going to rise. Now, number 2 and 3 are both going to start high and go low at varying rates. Now, the thought process behind this is we don't want them all the same. If they're all on top of each other, how would the control module know that these lines are not shorted to each other? So we're going to see that throughout Even in the example here of number 2, we can see one starts low, one starts high, and they actually cross each other as the pedal is pressed further. And this is a very common strategy here, but you'll notice that the lines definitely aren't shorted together because they're acting at different rates here. One little tip on this one is, it's kind of a good rule of thumb, if you will. The signal from number 1 and number 2 many times will add up to be 5. And so if we look here, on the example, signal 1 might be starting at 1 volt, signal number 2 might be starting at 4 volts, total of 5. And so you can see as they act each other, they cross at 2.5 volts. I verified this on a 2023 Chevy Traverse just last week. Yesterday on a Nissan Pathfinder, still really using the same type of strategy, many cases on the APP as well as on the TP sensors. Now, it's not going to be always. And so I'm always going to ask you to understand your own known good and look up service information. Manufacturers do a fantastic job of giving you the specs as to what these should look like, but just a casual observation through my own personal experiences here. There is another style, such as this one, in which they're going to both start low and work their way high as we stream throughout the sweep of the throttle here. But notice how they're offset. Again, the control module or the engineers need to know these are not shorted together. So they're both starting low and working their way high, just offset from each other. And that brings me up to another little power tip here. And so if you're going to replace one of these components here, it's very important to pay special attention to the electrical connector that goes with it. If I'm climbing underneath the dash to replace this thing, many cases, I'm going to always recommend to the customer that we're replacing the connector along with it. These things are inside the vehicle, but think about how close they are to the driver's feet. Now, if you're in a rainy situation or you're in the North Country where people are tromping through snow, remember they're putting their feet here. The floor is going to be wet. You're going to have a lot of humidity in this area here. And quite often we'll see terminal tension get relaxed or even what's referred to as fretting. And so sometimes even a technician unplugging and plugging this back in will create a different type of connection and somehow actually fix the condition there. We hate to fix a customer's car by simply unplugging and plugging something in. We want to make sure it's going to be a fix that lasts. And so if we're going to replace the APP, many times I'm going to recommend replacing the connector along with it. Otherwise, I'm going to recommend using a product such as this. So you might be familiar with Stabilant 22A. And so this stuff is definitely worth its weight in gold, literally, but it's a contact enhancer. And so if I can't get a connector or the customer doesn't agree to it, many times I'm going to put a few drops of the contact enhancer on here to help make a better connection to this. We certainly don't want to sell a customer a component and have them come back a week or a month later and say it's doing the same thing again. Never a good scenario. Now, if we look at the throttle body assembly itself, we've got a reversible brush DC motor. So our engineering test facility is on the other side of the wall from the studio here. So I walked out and grabbed a couple samples that they had sitting out there that they were installing on vehicles and doing some tests with. But if I remove the gear here, there's a little reversible DC motor. And so power and ground are applied to move it one direction. It's going to be reversed via the control module to drive it in the other direction. And then there's a set of gears here. So it's kind of a gear reduction setup, and the gears are going to drive and go to the throttle blade itself. Now, the throttle blade itself is going to have a spring acting on it to return it back to the default position here. But then inside, and you'll see actually in the cover here, this is a new Hall effect design TPS sensor. So there's multiple throttle position sensors here. Doesn't necessarily look like it, but there's different magnets inside of the throttle shaft here, acting across the Hall effect sensor, resulting in the output to the control module here. So if we look at these, we'll see kind of the default position. And if you've ever touched one of these or opened them up, you'll notice it doesn't just always go to the closed position. It's going to default to about the 7 to 12 degree range there. And if you drove a vehicle with a throttle body unplugged, it's going to run about 1,500 to 2,000 RPM. In some cases, for the name of research, I've even driven a vehicle around the block with a throttle body unplugged, and it drove surprisingly well because we're getting some air through here, but the RPMs can be controlled via cam timing, turbo, injection, quantity, amount, etc. So we're getting some accelerations and decelerations, even though the throttle body was left in its original 7 to 12 degree range there. So now if we start the vehicle up and the vehicle is idling, the control module is going to adjust the placement of the blade. And it's not always going to be the same. There's going to be different loads. Let's say AC system is on. It's a hot day. It's a cold day, whatever. We're going to see some changes there. And so it's going to be continuously adjusting it. And that kind of brings up another point here. We need to make sure that the throttle body is clean. And we also need to make sure that the idle position has been properly learned. And I'll talk about some tips on that in a little bit, but the idle position is crucial to good drivability or customer concern. Now, if the vehicle is going to accelerate, now the command is going to be given, power and ground will be applied to that motor. It's going to drive the throttle blade open in one direction. And then obviously it's going to go in the other direction to close it. So that brings me up another tip here. You can see I'm accentuating or moving the throttle blade here myself. Obviously this is in my hand, it's not on the vehicle. And so that's one of my cautionary tales here to you as a technician. When you're working on these things, it's tempting to just do it on the vehicle. I'm always going to recommend to remove it from the vehicle and do any actuation or any cleaning of it. For one, if you get it off the vehicle, you can access the backside, clean it much better. It's never really recommended to spray cleaner into here because it could wick through the shaft, actually short out the motor or the sensors inside of here. And so it's good practice to remove it from the vehicle. And now you're safe, right? If I put my fingers in there and the vehicle powers up somehow, or somebody's got a remote somewhere. I've had one finger sewn on at one time in my life. I really don't want to do it again by having a throttle body do some damage here. So safety first with this. One additional little tip as you're working on some of these, I've seen this in different forums, and we talked this in one of our GM classes years ago. If you actually hook a lab scope to some of these signals, they're going to be much different than what you expect or what you might find just on a scan tool itself. And so this is an example of some of the early model GMs, early 2000s, when they started getting into throttle actuator control systems. You would see that one of the signals would reference itself to ground, so it kept dropping off. And so unfortunately, in the forum I read it in, technician had the scope pattern. He was relatively new to scoping, and of course the comment was, the vehicle came in with this type of pattern. I replaced multiple throttle bodies. It's still doing the same thing here. And of course, this is a known good. And so just be aware of that. And that's another thing as we're testing and getting into newer technologies, we have to understand what known good is, have a good library, have a good network of friends to reference or contact, or, hey, can you share a known good pattern of this before falling down this path and actually replacing multiple components that are working properly, completely fine. So another little tip here, I hear this from some technicians too. Remember back in the days before drive-by-wire, you could pop the hood, you could actuate the throttle yourself. You could rev it up, grab the throttle, do all that stuff, or you'd press the pedal and you were ultimately in control of it. Well, remember in drive-by-wire systems now, we're not really in control of this anymore. The control module is the one that's in control of this. And so in the Buick, I've got it sitting in the bay here. If it was running or if it just sitting here key on engine off, if I step on the pedal, it's going to be limited throttle actuation. And so in order to do a complete test, many times I'm going to have to grab my scan tool here, and there's going to be a throttle body follower mode or a throttle actuation test here under special functions or active tests, which I'm going to have to enter that. That's going to control that throttle blade much better. And so be aware of that. Just because you're doing a key on engine off, foot to the floor and the throttle body moves like 30 degrees, that's normal in many situations. So don't replace the throttle body at that point. Take a look at your scan tool and see what type of output tests are available there. Next up is the torque manager, really the brains of the operation here. So as mentioned, we're receiving inputs from many different systems and looking at different pieces and different styles. And so we this is the one that actually makes the command to the throttle body and says, okay, do this, don't do that. And then ultimately the engine's going to generate torque and apply it to the wheels. A couple little tips here. GM failure modes is some acceleration limiting or limited throttle. These are different modes in which the vehicle will operate. And this is one of the frustrating things I think for technicians as we're working on these things is I can remember when I was a technician at the shop, we were fighting an intermittent problem. And so there would be force or engine shutdown mode. And so we would get into force idle mode and the customer would say, it's doing it right now. Well, no, really the problem happened 5 miles ago. You're in one of these various shutdown modes here. And so the symptom or the problem really only happened for a couple tenths of a second, but now it's actually really occurring here, or you're seeing the fallouts from it. A couple scan data PIDs here that working on GMs, I'm always going to encourage is looking here at APP 1 and 2, make sure it agrees. TP 1 and 2, make sure that it agrees. TAC communication and understanding that and taking a look at that. Throttle body airflow compensation. And so we want to take a look at understand what this data PID is doing and how it's actually working here. And so we need to take a look at this. Throttle body idle airflow compensation is a very important PID. As that throttle body starts to get contaminated and dirty, it's going to have to open that further and further and move it up more and more here. And so that's a great technician tip. If that number is significantly increased from what you're used to seeing, like 35, 40%, that means you've got a dirty throttle body or a worn out throttle body. It's having to work a little harder. TP sensor learn minimum, that's going to change when you do the relearn process with your scan tool. We need to understand what a known good or the learned value is and how it stays there. Throttle actuator motor command, and that's a very important tip on General Motors vehicles. And if I look at it here on this particular Buick that's in the studio with me, I'm not going to see anything because it's in key on engine off mode right now. But if the vehicle is running, let me pull up a scan capture here. And this is from a case study, which ultimately had a worn out throttle body. So as we look at the different PIDs here, we can see TP desired angle, we can see APP indicated angle on the bottom, but we see that red noise on the top there. That is the TAC motor command given to us in a percentage. And that's the benefit of graphing scan data. As we work through this, we can see all the different stuff happening here and all the different pieces. So again, experience tells us this. Imagine if you're a scope guy and you put a current probe on the motor side of a throttle body. That's really what this data PID is doing for us. And so even with the vehicle at idle running in the bay, it's going to be doing some type of compensation at all time. And that motor is going to be putting in some work. And so if we look at this one, and again, this is where experience comes into play, but you look at that TAC motor command PID as it's graphed out here. Let's go ahead and replace the throttle body and let's look at the new data. I think you'll agree it looks much cleaner, much less effort required here. And so as a combination of some buildup, but also worn teeth. Remember I showed you those gears in there are doing some additional work. And so that's a result of this. So next time you're working on a GM electronic throttle controlled vehicle, I'm going to encourage you to look at that TAC motor command data PID. So let's look at some diagnosis here. And really, these systems are relatively simple. Yes, they're frustrating and a lot of stuff happens in a millisecond that puts the vehicle into FMEM or some type of failure mode. But really it can be broken into the three systems. I've talked about APPs, control modules, and the throttle body itself. And the codes are very much similar to that as well. So as I look at the schematic on the screen here, you can see the APP signal. We've got the multiple APPs there. Same thing on the throttle body. We got the motor command here, which will be reverse polarity to drive it one way or the other. Then we've also got the two throttle position sensors there, all as inputs or outputs from the engine control module. So many times when a technician gets a throttle position code, not a whole lot of reason to pay attention to the APP system at this point. Follow where the trouble codes lead you down the path here. So in the example here, and let me pull up the scan tool. So I've got it plugged into our Buick. And so as we take a look at it here, I'm going to pull up the DTCs or the trouble codes that were set with this. Now, keep in mind, we do a lot of hands-on training here at our training center in Texas. We've got our engineering test lab right outside. And so a lot of people are poking and prodding at our vehicles here and stuff happens. So if we look at the scan data here, you can see I've got throttle position sensor 1, circuit low voltage. Also got a code for throttle close position performance. And then I've also got a code for throttle position sensors 1 and 2, not plausible. Now, again, which one of these makes the most sense to follow? Well, I'm not too worried about throttle position sensor 2 because I've got another code that points to TP1. And so if I back out of this, I can look at scan data. Let me pull that up here a second. I know we're kind of running somewhat short on time, but I want to get through some of this and show you just some of the data that's available to us on the throttle side. So you can see reduced engine power. Again, the vehicle's key on engine off sitting here in the bay. So a lot of stuff will be at 0, but you'll see some of these agree and disagree. Oh, look at that. My 1 and 2 disagree. Now I can look at my voltages, run through some of this. My learned minimum, my throttle body idle airflow compensation percentage, it's 44%. The vehicle's not running right now. That is higher than I like to see on many of these. Throttle system performance tests, MAP, mass airflow, force engine shutdown. Yes. So we've got a true problem here with this idle engine speed, TAC motor command. Right now it's showing 0 simply because the engine is not running. But again, based on this information, my trouble codes are talking about throttle position. So am I going to go underneath the dash and lay on the grimy floor and worry about the APP? I'm not. I'm going to simply focus on the throttle body or the throttle signals here. So if I go over to the vehicle here and take a look at the car, you'll notice that I've already got a lab scope hooked up here. And so we look at the wire schematic shown. You can see the brown and the green trace is my TP1 signal here. And so again, based on what I know about this vehicle and the amount of poking and prodding that's been done here, I'm concerned with the wire harness itself. And so I'm suspecting we might have something going on. The PCM is solid mounted to the vehicle itself, and then the engine is going to be rocking via the motor mounts. And so sometimes we see that manipulation of the harness itself. So if we take a look at this slide here, I just grabbed a quick snapshot so you can see closely where my scope connections are. And again, guilty as charged. You can see I'm using some probing connections here. So I am piercing the wires slightly. And if that's done enough times on the same vehicle, we could result in a problem here. So let me take a look at the scope here. So again, I've got the lab scope hooked up. I'm looking at Pico. I've got channel 1 connected at the throttle body, and I've got channel 2 connected here at the PCM. And so you look here, my voltages are, or my scales are 0 to 5 volt. On the left is the blue, and on the right is the red. And so this should be the exact same, but look at how that signal is wavering here. I'm looking at the exact same circuit. It's not like I'm looking at TP1, TP2. I'm looking at the same thing, and look at how that signal disappears. All of a sudden now it's perfectly matching. It is right in line. See, it's even hidden behind. Now it drops out. And so as I touch this harness, all I have to do is touch it or give it a little bit of a wiggle. Look at how the signal is dropping off as it's returning to the PCM. And so I think I've just verified that this is truly a wiring issue here. Yes, I might go ahead and go back to replacing the throttle body, but hopefully you get a little bit of understanding from that itself there. Now, how we've kind of tested this and understand what's gone on with this. Because of what I've already put in, remember that the airflow compensation PID, I'm suspecting this throttle body is pretty dirty, might be coked up there. And so at the very least, I'm going to go down the path and look for a wiring fault now. I'm going to at least clean up the throttle body. If available, we're going to replace the throttle body here. Let's do it right. So here's some important steps for you as technicians as you're diagnosing these systems. First off, we always need to verify the customer concern. Customer brings their vehicle not because they're sick of it being at home and it's a great inconvenience for them. There's a problem, right? They bring the vehicle to you. We need to verify that it is doing what the customer said it's doing. But it's important to take your scan tool with you and record the data while you're test driving it. It's sometimes hard to focus on this stuff. Sometimes we need to trim out some different data PIDs, but we want to record it. No sense in going, oh yeah, the car acts up, I caught it, but did you catch it? If you don't have a scan tool recording data, did you catch it? Next, we're going to bring it back into the shop. We're going to do a visual inspection. That's what really led me on this path. I'm like, somebody's pulled some of the covers off here. I can see where somebody's been here before. That might be the direction I'm looking at here. Now we're going to pull DTCs. So in this one, we had throttle related trouble codes. I don't care so much about the APP. It could be a module processing issue yet, but right now the codes are pointing me towards the throttle side of the equation. That's where I'm going to spend my time. Now we're going to do some research. Now I want to see if there's any technical service bulletins. This is a common issue. Is there any software updates? And do we need to fix it with a reflash? Many vehicles in my career I've fixed with software updates there. You need to understand the code setting criteria. What conditions does it have to be in to make the trouble code set? So if I couldn't verify it, how do I test in those same conditions there? Now is when I'm going to analyze my recorded data. Did I find the fault in my data? Sitting behind a desk at your workstation is much more easy to analyze it than trying to drive down the road and keep an eye on things. Now I've got a game plan together, such as here, I got the wire schematic together. I understood the conditions. I understood the trouble code. I had a pretty good game plan before I really popped the hood and started digging in here. This is where I decided, all right, I'm gonna hook my lab scope here. Maybe you don't have a lab scope. You can try it with a DVOM. A lot of these things happen so quickly. I'm not sure if the meters are going to catch it there. With a test light only, you might be a little bit more of a struggle there. But if you've been thinking about buying a lab scope, this might be the excuse to nudge you there to learn that art or that craft. So then we're going to make the repair, whether it be replace the component, fix the wiring in this example. And now we need to do a throttle relearn. Now, different vehicles, such as Nissan, we call it the hokey pokey. You have to have a stopwatch. It's very difficult. It's very specific and very time intensive in which you have to do that relearn. Some of these GMs here, there's 3 different relearns I can do with a scan tool. Some Fords back in the early systems, they had a set procedure. You let the vehicle warm up, let it run for 2 minutes in this condition, turn the AC on for 2 minutes in this condition and go through that. But it's very important to look in service information to understand what relearns are required for the vehicle that you're working on here today. And then we want to make sure that the problem's been solved, right? Customers are trading us their hard-earned money for us removing the pain from them. The pain here was the check engine light was on, the vehicle going to reduced power mode. And so if I'm going to take compensation for repairing something, we want to verify it. We want to make sure that it's been done properly. So we feel confident in giving it back to the customer, and we're not going to get a repeat phone call for the same problem very soon. So that kind of wraps us up here. I just want to kind of thank you for coming. And if you're looking for more information, we do have a full-blown standard pro training class available on torque management and throttle control. We also have our YouTube channel. So you can go to Standard Brand YouTube channel. You can search Throttle, and there's different playlists, different installation videos, different diagnostic and theory videos that you can access there. If you learn more about the program as well, you can go to standardbrand.com. You can learn more about our newer and improved, never remanufactured electronic throttle bodies, even the APPs, some more about the systems here. So again, my name is Ryan Koyman. On behalf of everybody at Standard Motor Products and the S&P Pro Training team, I appreciate your time here. And Corey, do we have any questions that have come in?
Just one question. It's a good question. What is the part number on the Stabilant 22?
That is a great question. I would go ahead and just Google Stabilant 22A, and you can find it through many part suppliers. It's probably a little known piece, but it is a fantastic product, a contact enhancer there. So Google Stabilant 22A, and you should be able to find that. So thanks again for tuning in. Until next time, happy diagnosing.